Hi, Jasmine. I've got your question here up on the screen, the graph that you sent me. There's not a lot of information here, so I'm going to try to just sort of give you some general information about the t-test and interpreting it, and I'm hoping that that will help you with your assignment. Um, um, what I'm missing is, sorry for the confusion here, but what I'm missing is things like n, the number of things in the sample, and things like that for the analysis of this. If this was all you were given, then there are just some sort of general conclusions that you can take from it. So let me just make this a little bit bigger so we can read it better here. According to the information in the graph and from what I read from the paragraphs that you also sent me in the screenshots, which is really helpful, thank you. Um, what we're doing here is it looks like we're doing a two-sample t-test, and we are comparing the means of diameters of gulls and flies, whatever that might be. And it looks like what they've done is they've run the t-test, and you said it was a Welch's t-test, and that this is what they're reporting in terms of the t-value and the p-value after they ran that test. So if we talk a little bit about those two values, what we're generally looking at when we're doing these types of tests is we start with a hypothesis. And I think that you probably already have that part of it understood according to your question. We have a null hypothesis and we have an alternate hypothesis. And the null hypothesis is that for all intents and purposes, everything is the same here, that the two samples are equal. So we would write that as mu1 equals mu2 in this case. And in this case, I don't know how it was phrased, but the normal two ways of writing an alternate hypothesis are either to say that the first mean is not equal to the second mean. That's supposed to be a mu there. Or if it's important that one thing is higher or lower than another, then sometimes we might write that, the first mean is greater than the second mean or something like that. And that would be like in the case of, like a simple example would be if we're trying to compare test scores for two different classes because we think that one teacher's maybe better than the other or something like that, then we might say that, Class A's test scores are significantly higher than Class B. And so in that case, it actually matters because we need those marks to be higher than Class B if our hypothesis is correct. So again, I don't have the information from what you've sent me. I'm not really sure if they're asking you to say that it's greater than or less than or equal here. I think it just says with one mean and standard deviation substantially higher than the other. I think that they refer to that in terms of defining what a statistical difference would be, and that is, what we're looking for when we say, aha, there is a difference between these things. Because in statistics, having two things be the same doesn't mean that they're equal. It just means that they're so close that basically there's no difference. So equal doesn't really mean equal in statistics. From the information that we've got here on the graph, when we've got a t-value of, I think that says negative 0.97, and a p-value of 0.351, that p-value is way high. If that's a p-value, then the p-values are usually around 0.05. That's a 95% significance level for a hypothesis. Sometimes it's smaller than that if we make it like a 99% significance level. Sometimes it's bigger. If we make it a 90%, it would be 0.1. But 0.381 or 351 is just really large. And so what that tells us from these results is that your values, when you're comparing your two means, I think that you're probably familiar with the z-test. I hope that you're familiar with the z-test. If we just go back to the normal curve for a minute and compare it to that for a second in terms of a z-test, when we're comparing two means, what we're doing is we're getting a z-score, which is our critical value, and we're comparing it to the z-score between the two means. And if it turns out that both of them are in this general area of the curve, then we say, hey, they're equal. They're where most of the population is. If it turns out that they're in this part, which we call the tail, then we say, hey, something significantly different is going on here. When that happens, usually what we have done is set it up so that this tail represents 5% of the population. And if it's a two-tailed test, we would split that 5% for the left and the right-hand side tails. So you'd have one down here and one up here, and they would each be 2.5%. So if the score that you're looking at, if one of those scores that you're comparing lands in this region and the other one is in the red region, then we say, wow, those are significantly different. If both scores land in this main red region, though, we say, nope, they're the same. So that's what you're trying to interpret based on what you're being given here. So when we look at our scores and we look at the p-value, already that p-value is telling us that these scores are not statistically different. One of them has to be in that sort of critical range in those tail parts of the curve in order for it to be statistically different or significantly different. And that's not the case here. If we have a p-value of 0.351, it's just too big. And so when you're looking at the graph itself and you're looking at the means, it looks to me like the dead have a mean of about 16. This would have been a good Halloween assignment. It looks also like the alive have a mean of about 17. Now those are pretty close, but what really determines how close they are is your standard deviation. And that's what the line part of these bar graphs or box graphs are. It looks like you have an SD, a standard deviation of about 2, because it looks like we're going from 14 to 16, so that space looks to be about 2 on this graph. And the same thing here from 17 maybe down to just over 14, so let's maybe call it at 2.5 or something. But the standard deviations and the means are very, very similar here. And so I would conclude from looking at this graph without any further information. Like I said, I don't have n, so I don't know if it's a normal approximation. There's a lot of information missing here, but just based on what we do have, I would conclude that this is a case of the two means being, I would say that the null hypothesis is correct. I would fail to reject the null hypothesis is how I think you guys are doing it. I would fail to reject because they are too similar. And the only time that we reject the null, in other words, the only time that we say they're not basically the same, is when they're significantly different, which has to be one of them in this tail of the graph. Okay, so I would accept the null hypothesis that both of these means are basically the same. There's no significant difference between the means, between the dead and the alive. So I hope that helps. If you need any more clarification on any of these tests and things like that, feel free to email me back and I'll try to provide that information for you.